Welcome to the third presentation in the fourth webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We thank everyone for attending the webinar today. The webinar series has been an immense success, and the recordings of previous webinars continue to be viewed on YouTube and Bilibili. This is the third webinar of our fourth series, which we will continue to have monthly throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the fourth series will be distributed through the IAS mailing list and the IAS Twitter feed. Today's webinar will be given by Professor Alissa Park at Columbia University in the United States. I'm Nicholas Wilkins at Sfonte Technologies Incorporated. Today's webinar will be moderated by David Donacci at Imperial College London. We are required to remind the attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you are not already. Our dues are minimal, only about $20 US per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants, and workshop seed funding for IAS members and affiliated groups, as well as aid in the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @intadsots for future updates regarding IAS events, webinars, and information about scientific meetings. Please help us expand our YouTube channel by liking this video and subscribing. I'll now hand it over to David, who will moderate the YouTube Q&A.
Thank you very much, Nick. It's my pleasure today to welcome Professor Alissa Park to the webinar. Professor Park is the Lenfest Earth Institute Professor of Climate Change in the Departments of Earth and Environmental Engineering and also Chemical Engineering at Columbia University. She is also the Director of the Lenfest Center for Sustainable Energy. Her research focuses on sustainable energy and materials conversion pathways with an emphasis on integrated carbon capture, utilization, and storage technologies. Professor Park received a number of professional awards and honors, including the Shell Thomas Barron Award in Fluid Particle Systems at IKE 2022, the ACS ENFL Mid-Career Researcher Award in 2022, the US C3E Research Award in 2018, the PSRI Lectureship Award at IKE 2018, and the NSF Career Award in 2009. Professor Park has also led a number of global and national discussions on CCUS, including the Mission Innovation Workshop in 2017. Professor Park is a fellow of the American Institute of Chemical Engineers, the American Chemical Society, the Royal Society of Chemistry, and AAAS. During the webinar, questions can be submitted to the speaker in the YouTube live chat, and I will moderate those at the end of her presentation. So with that, I'd like to welcome Alissa Park and pass over to her.
Thank you, David. Can you hear me well?
Yes, can hear you well.
All right, let me share my screen. All right, can you see my screen well?
Yes, seems to be working fine.
Wonderful. Give me 1 second. Move myself down. So, hi everyone. It's great to be part of this wonderful webinar series. I was really enjoying other webinars and on various topics. And today I'm really excited to talk about some of our research and my colleagues' research in the area of carbon capture and conversion. And there are a lot of interesting materials and absorption behaviors of those materials in these areas. In particular, I'll be talking about today liquid-like nanoparticle organic hybrid materials. We call them NOMs. I guess I don't need to talk to you about the carbon dioxide is an issue at this point. And I think you've seen all these discussions over the decades, not years, decades, on how CO2 concentration in atmosphere is linked to climate change. And in fact, in recent years, you see these extreme weather conditions, droughts and floods and fires and many other things really impacting not only the large global scale climate change, even locally impacting human lives tremendously. So we've been working on this as scientists and engineers for about 3 decades intensively, how to do the carbon management throughout our natural and industrial systems. Some of you have seen this important figure, I believe, that when you have some positive emissions of some pollutants, for example, in this case, we are talking about carbon dioxide in atmosphere, we are really challenged by that concentration. If you know, for example, coal-fired power plant or natural gas-fired power plant, what would you do if there's a positive emissions, which is happening today? You go to that emission point and stop that emission. And basically that's going from positive emission to zero emission. And that is very important at this point. But if you look at this figure on the right-hand side right here, there's something called negative emission technologies, which we started talking about a decade ago. Basically, what he's saying is the entire discussion on climate change and carbon management, we all agreed that not only we need to go to zero emission, but also we need to do deep decarbonization towards the negative emission technologies, which means that not only we're going to stop the current emission, but we're going to go back into our history and pick up the CO2, which has been emitted historically in decades and century ago into our atmosphere and take that out of the atmosphere and putting it away. That's what it means by negative emission technologies. As you can imagine, this is a very daunting task. And a single solution not going to make the negative emission technologies. We need to look at all the options and technology development in order to achieve that. In the United States, so in particular, since we are talking to the global audience here, that we are really, the current government, US government is really serious about not only zero emission technologies, but also negative emission technologies. So within US government, we have an office called the US Department of Energy, and within Department of Energy, we have Office of Fossil Energy. For over the last 30 years or more, Fossil Energy Office been really supporting a lot of research in the area of carbon capture and storage and even utilization. And as new government came in with Biden, we actually changed the name of this office to Office of Fossil Energy and Carbon Management. I think this is a really big statement because you're not going to change the name of the government office within Department of Energy just for a solution we need to fix, like if it is just Band-Aid for the next 10 years or so. Basically, this is a stating that carbon management has to be fully integrated into our energy systems and material systems and for the entire future. This is a new norm, not a short bridge for us to achieve the sustainable energy. Not only they talked about just changing the name of the office, there was very interesting discussions and also support going into fundamental R&D all the way to infrastructure installment and development. This is the something called Energy Earthshot initiative, which has been announced starting to mid-2021 by Secretary of Energy in the United States. The entire goal is right here, net zero economy by 2050. This is a very ambitious goal, but I think it's really great that we have ambitious goal. In order to achieve that, this is not only net zero, we are going to net zero economy beyond the power sector. And in order to achieve that, the first energy Earthshot, which was announced in mid-2021, was all about hydrogen. The target is $1 per kilogram of hydrogen in 1 decade. Very ambitious goal. Some of you working in hydrogen, you know what is the price of current hydrogen price. And not only this is ambitious because it's a quite low cost and economically very challenged, and as well as technologically, but this should be kilogram of hydrogen which is carbon free. And that will be very important because it's really tied to other sustainable energy initiatives and goals, including the third energy Earthshot, which was announced in November 2021, which is all about carbon. This carbon negative energy Earthshot aims to get $100 per ton of CCUS, entire carbon management scheme. And again, this ultimate goal is towards the net zero emission by 2050. So not only they're having all these goals, they're putting a lot of fundamental research funding as well as funding for installing infrastructure to support all these. So I think we have really great energy and motivation and aims and challenges and opportunities toward this area. So we are really at the right time and right place to deploy it and or develop our technologies. So let's talk about how to capture carbon. This is how we've been doing in the large scale for quite a number of years. This is a Petronova project, which is one of the largest demonstration projects for carbon capture, which was installed in Houston in the United States. If you look at the photo right here, which I actually took in 2017, there is a large CO2 capture and solvent regeneration column, which is not even a full scale, I believe, in this particular power plant. They were capturing more than 1 million tons of CO2, and they stopped in 2020, but they will be resuming their operations soon. The particular material they targeted on is the material which has been mostly studied, which is a liquid amine solvents, which is the aqueous water-based liquid solvent system. And it's a chemical reaction. So you're doing catch and release by doing the chemical reaction with the amine with CO2, making carbamate. And then you're regenerating the solvent in this red colored reactor, which is solvent regeneration column, by putting energy in so you can release the CO2 and regenerate the liquid solvent, which you can recycle back into CO2 capture reactors. So you can imagine that if you have a strong binding energy towards the CO2, your reactor, the green reactor, which is CO2 absorption column, will be faster reaction kinetic and smaller. But at the same time, stronger the binding energy, now you have to pay that energy penalty in this regeneration reactor to release that CO2 back out. So there should be some optimization between how strong that binding energy has to be. And that's why we've been working on quite a bit on amine functional groups, because amine is pretty good at capturing CO2, but also not too strong, so that with the minimum, optimized energy somewhat in moderate energy requirement is needed to regenerate this solvent, which is about 120 to 140 degrees C of heat we can provide. So looking at all these, we learned so much about how fast this reaction kinetic is, how selective this material is. And it's very easy to move this liquid solvent around, pumping them around, designing reactors. So there are a lot of benefits. At the same time, even decades ago, we kind of estimated that the amount of energy needed to do that solvent regeneration is quite high, so that the amount will be, in terms of, for example, coal-fired power plant, which does not have a high efficiency in the United States because we have really old power plant, it will reduce the power plant efficiency by 1/3. Which is really significant because our power plant efficiency was about 34–36% even at the time. So either you produce 1/3 less electricity, or you have to burn 1/3 more fuel to make same amount of electricity. So this is a big challenge. I'm not saying we should stop using these liquid amine solvents for the CO2 capture. Definitely, these are one of the well-studied materials, and I'm sure we can do better heat integration to make this a lot more efficient overall. But at the same time, we also realized that having all that water, 70 to 85% of these liquid solvents is water coming along the ride, just heating that water up and cooling it down between these two reactor systems are a lot of energy penalty. So people start looking into second generation CO2 capture liquid solvents. I'm talking about liquid material at this time. Those are mostly water-lean or waterless CO2 capture solvents. So one of the good examples, in addition to ionic liquids and cobalts and other things, are the materials I started working on about a decade ago called NOMS, nanoparticle organic hybrid materials. In fact, this particular material was developed by Lyndon Archer and his colleagues at Cornell University. And Lyndon called me one day and said, Alissa, we made really these interesting materials by tethering polymers with the right size, right grafting density onto nanoparticles. The final product is, as shown here, is a liquid-like material. And what he said was, this is really interesting because there's so much chemical, physical tunability. At the same time, it has almost zero vapor pressure and very thermally stable. So I thought it was really fascinating material because we have to do a lot of temperature swing and thousands cycles for CO2 capture, so that if I can decorate all these materials of NOMS with a lot of amine functional groups, perhaps we can make a material with the waterless, but still behave like liquid-like material for CO2 capture. Not only that, we will make this material such that the tethered polymer will have a very different structure, hopefully. By doing so, we can have not only enthalpy with the amine functional groups, but also entropic contribution towards to enhance CO2 capture. So first generation of these materials was these two examples shown here. These are the NOMS on the right-hand side, tethered with HPE, and then on the left-hand side is just a polymer, unbound polymer we started with. What we wanted to see was by tethering them, do we really change the structure of these materials or polymers, which is present in these liquid systems? This is a 2D rosy NMR, and the only thing you kind of need to know is between left and right spectrum, there's a lot less signal on the right-hand side, which is kind of showing you that the interaction between different functional groups within the system is a lot less. What it means is that tethered polymer here in NOMS compared to untethered polymer, they were more stretched out and far away from each other, in a sense that creating a lot of free volume in between. So we were kind of showing that we can, by tethering polymers, we can change the structure conformation of the polymer itself and also distance between polymers, creating very interesting cavities for free volume. So next thing we really checked was, do we really, why or do we improve the thermal stability of these materials? On the left-hand side, simple thermal, looking at the thermal stability of different materials, untethered polymer degrades pretty relatively quickly, about 200 degrees C, particularly this PEG. But then by tethering them, we can expand this thermal window by almost 100 degrees. But it becomes even more interesting if you look at the right-hand side figure. The over 100 cycles, NOMS are very, very stable compared to untethered polymer degrade almost 80%. So for CO2 capture application, we need to use these materials for thousands and thousands cycles, as I mentioned, to be economical. So it was very important for us to use the NOMS, which gives very, very good thermal stability. And in fact, I don't think I'm going to show the data. The oxidative thermal stability of NOMS was much better than any of the polymer which was untethered, which is very important for our systems for CO2 capture. So now only thing we had to do was decorate all these materials with amine functional groups. And as we expected, each time we load more amine to the system, you have a huge increase in CO2 capture capacity. And it was in some cases even better than state-of-art 38% MEA solution. But After that, now we had to think about, we've been making these really wide range of interesting materials at very, very small quantity in the lab. But do you remember all those big, huge reactor systems I was showing you earlier on from Petronova project? We need to make these in tons and millions tons of these materials, and then we have to design the reactor, put these in. So one of the first things we did after checking all the selectivity and capture capacity was viscosity. Viscosity is very important when you try to design any of the reactor systems, which now you need to make sure that there's no mass transfer limitation or even heat transfer. If you look here, the bottom data set is MEA solution. As you can see, very low viscosity, very easy to work with, and there are many different designs of reactors you can make. Their second groups are ionic liquids. A lot of colleagues like John Brennick is working in this area, how to reduce the viscosity of ionic liquid to really have easy heat and mass transfer. Their top groups right here, these are just some of the examples of NOMs we made, and they are definitely highly viscous. And when I looked at this data again, this is the log plot on the y-axis. So we realized, oh my gosh, this is really, really, really viscous. So I started thinking about this. It's basically, we're looking at like a thick honey-like material, and we're gonna try to use it as a liquid solvent. At this viscosity, there's no way we're gonna pump these materials. It'll be extremely energy intense, and not only that, it'll be just almost impossible. So we thought about this quite a bit. Ionic liquid colleagues, and we also did a little bit of that, is that you can really control the hydrogen bonding network of these materials to really reduce the viscosity. But looking at our materials, maybe not. We are way beyond that level, we thought. But I kind of went back, like we still like this material because almost near zero vapor pressure. There's a lot of chemical and physical tunability. If only thing we don't, or we have challenge of, is the heat and mass transfer of this thick viscous fluid. What if we can somehow chop up these thick fluids and package them apart? Maybe we can create a lot of interfaces without worrying about all these viscosity issues. So that's when we start working with Lawrence Livermore National Lab colleagues, Roger Ains' group. And what they did was they were preparing micro beads, having a lot of carbonate solutions, doing bicarbonate-carbonate swing for CO2 capture. So instead of putting carbonate solution in there, we thought, well, why don't we put highly viscous our fluid inside? So if you look here, this blue fluid is just blue, with the blue dye, we put NOMs inside, and this white fluid is UV curable polymer. So you create the droplet inside a droplet, and then in the second stage, you can UV cure, which cures only this UV cure polymer, which is in the outside layer as gas permeable layer. And here are some of the examples of what we actually made. You can see that we can make single core, multi-core of a lot of these materials shown on the right. And we intentionally made these particles not a nanoscale, because you can't really deal with nanoscale particles easily in reactor systems. But we were making the 300, 400, 500 micron size much easier to design these particle systems for either duct injection or fluidized bed reactors, or even fixed bed, depending on the applications. And by tuning the thickness of these gas permeable kind of membrane-like shell, we were able to let CO2 in very quickly. So as we expected, compared to neat NOMs, we really increased the CO2 capture capacity, kinetics of CO2 capture tremendously. But as going back to here, you can imagine that single core versus the multi-core will have a lot more interfacial area, and it will enhance the rate of CO2 capture even fast. So we decided that, well, 3D microfluidic device is great doing fundamental research, but scale up of these systems will be harder. So we start thinking about what is the way to scale up producing these microbeads with the liquid droplets inside, and while making liquid droplets as small as possible. So next generation of materials we made was something called SIPs, solvent impregnated polymer. This system is very simple to make. So what we do is start with the UV cured polymer, and then we put our NOMS material, which is viscous, mix them together, but use high shear to make sure that we made emulsified system. By doing so, we can make sub-micron droplets, and then you can cast them into flat surface and UV cure, and you can make different shapes and sizes of particles by grinding them. So here are optical microscope after making them emulsified. So from about 10 weight% all the way to 50 weight% loading of NOMS. And as you can see from the lowest loading, you see small droplets, but by the time 50% is almost like a well-mixed system. After UV curing, if you look using naked eye, you can see them as if it looks like just a polymer film. But then if you go inside, really zoom in, there's a sub-micron droplets of NOMS everywhere. And as you can see in EDS mapping, you see nitrogen everywhere, which is associated with NOMS. And because it was well distributed and very, very tiny droplets, sub-micron droplets, our CO2 capture kinetics were significantly improved further. So it worked really, really well. While looking at this, we have to think about what do we do once we capture carbon dioxide from various sources, including power plant. If you do care about climate change, you have to store. You have to store as much as possible because the amount of CO2 we are emitting today is so much that we cannot convert or utilize all this CO2 into some useful product. So you need to do both, but the majority of carbon dioxide has to be stored. Unfortunately, the amount of CO2 we are emitting or capturing should be so much in gigatons so that we cannot build storage tank large enough to store this carbon dioxide. So in fact, we went back to the Mother Earth and say, well, let's see whether there is a large enough storage tank to inject CO2 in pore spaces underground. And fortunately, there are enough of these pore spaces, and we know how to inject this CO2 quite well. And what would happen, the pressure and condition of CO2 being injected is about 150 atmospheric pressure. And as you inject, as shown in the right-hand side figure right here, it goes through 3 or 4 different trapping mechanisms, starting from having a strong cap rock, non-permeable cap rock. You're kind of keeping them as a plume, and this high-pressure CO2 now goes into the pores and then start to dissolve in water layer, and that's what happens over the years. This is a really famous Sally Benson schematic showing that what happens to the injected CO2. But one thing you may have noticed, something's missing in this figure. On the x-axis, there are no numbers. So we really did not know how long it will take. Would it take 2 years, 5 years, 10 years, 1,000 years, or 100,000 years? We really do not know. And is really depending on which site, injection site we are talking about, what are the geological formations. But one last thing showing here at the bottom right is something called mineral trapping. And that's very interesting because carbon in the form of fossil fuels, resources we've been using and kind of converting them to carbon dioxide, we've been utilizing all that energy difference with whatever efficiencies we are talking about. There are only very few downhill reactions, and making solid carbonates like limestone is one of the natural process going thermodynamically favorable downhill. So people then start looking at, well, when can we enhance that reaction over the years? And in fact, one of the really interesting studies done a number of years ago is Carfix in Iceland. They actually injected the carbonated water in porous geological formation into pore spaces, and they were able to create these crystals, and which is very interesting within 2 years. And there are a lot of mine tailings now you can use to convert CO2 to solid carbonates, and I will be revisiting this photo later on in this talk. But there was also a very interesting report that came out in 2020, mid-2020 by McKinsey. And they estimated by 2030, which means that they were looking at 10-year projection. Now we only have 7 years left. This is a light gray bubble showing that how much carbon storage we may do. I'm really hoping that they underestimate it, because for climate change sake or climate change mitigation, we want this gray bubble to be as large as possible. But at the same time, there's a very interesting black bubble, which is quite compatible size to predicted the storage potential. They predicted that by 2030, we'll be making fuels, construction materials, even plastics and chemicals from captured carbon dioxide. This is very ambitious goal, or very interesting prediction, very assuming that there will be a market for these things and it'll be economical to make like even fuels out of carbon dioxide. Looking at where I am, this is in New York City, and we also have a lot of chemicals and materials shown at the bottom. And I think some of you maybe used it today, this morning, you use shampoo or some other things. If you look at these materials, can we decarbonize these chemicals and materials and infrastructures? Yes, and I hope so, we do that. But at the same time, if I ask you, can we completely decarbonize? That answer is no, because we live in a carbon-heavy society. Carbon is a critical building block for all the things most of the things we use and we need to utilize. So in a sense that we need to have not only decarbonization, but we need defossilization of chemicals and materials. When I first used this term 2018, defossilization, there was a lot of pushback from energy companies, because there are a lot of stakeholders are very interested in their asset in fossil resources. But recently, the energy companies start really using defossilization, understanding that our society needs carbon. As long as that carbon is not from fossil resources, we might be okay, which means we really need a lot of renewable energy to support all these things we need. So that leads to a whole new circular carbon economy. So there's a chemicals and materials and fuels we use, and there's a consumer market, like some of us, all of us doing end users. And hopefully the way we use carbon or other resources and materials and chemicals will lead us to capture that carbon back into our new circular carbon economy, which will have only input of renewable energy and hydrogen. And we need to learn, or we need to develop this technology to capture CO2 effectively and convert them, which might require more than one technology. It could be thermochemical, electrochemical, or photocatalytic, or even bioconversion, or into hybrid mode. But one thing you really need to remember is that this is core new circular carbon economy at the commodity chemical level, because we're going to change the entire chemical industry. So tech to market will be very important, as well as economics and policy. One thing I'm not going to talk about today, but it's important, is which hydrogen are we going to use as a core product? Because you can do all the carbon, circular carbon economy, but if this particular hydrogen we use has high carbon intensity, it will not work either. So what is the magic hydrogen? Apparently there are many different colors of hydrogen. There's a black, gray, blue, green, pink. The latest color I heard is orange. So it's really important to find the right color of the, select the right color of the hydrogen, because that is associated with carbon intensity. So let's think about how to make circular. Which carbon should we use? So as I told you, it has to be non-fossil carbon, and also this has to replace entire commodity chemical, means we need to have a lot of these. So let's go big as possible. So if you want to be really large, you have gas, liquid, and solid. Let's think about that. What is the biggest body of gas? It will be atmosphere. What is the biggest body of liquid? Ocean. And biggest body of solid will be rocks and mountains and soil and all that. So let's not touch the one in soil, because that one maybe can be already stored away carbon, so that we don't want to, for example, burn limestone to harvest carbon for our chemical industry. I don't think so. In some cases, maybe, but not in this particular case. So we have option of air and ocean, and there's a delicate equilibrium between atmosphere and ocean anyway. So these are coming hand in hand. So you can actually develop technology to directly harvest carbon from air and ocean. We call them direct air capture and direct ocean capture. You can also go through biomass routes, so that you can go from air to biomass and then use that as a carbon source that can be terrestrial or marine biomass. These are all the options. And is it harder than using fossil carbon? Definitely, because the fossil carbon always come with high density of energy coming along, so we can do a lot very easily. But that we already determined is not sustainable. So although it will take a lot of energy, hopefully renewable energy, to get to these, but it's really important for the future to be circular, to harvest carbon from air and ocean, or either directly or through biomass route. So let's talk about direct air capture. Many of you are already working on this area. Tremendous effort is happening last 10 years, especially, but there are a few of us out there, including Chris Jones and Klaus Lackner, been working on for at least a few decades on this area. CO2 capture directly from air is a very different challenge. And in fact, because of that, that development has been quite different. This photo on the top left is the Climeworks system in Switzerland. This looks very different from the one I showed you from Petronova project. The Petronova project is huge single unit, which really benefit from economics of scale. But at the same time, it was really hard to keep building many of these Petronova projects to learn from each generation. So you need to really build that, and it takes really long time and high capex. But these systems, traditionally direct air capture systems, has been developed as a modular system. A person will be similar size as this single unit, which is we do copy paste and copy paste, which is instead of scaling up, you're doing scale out. So you can benefit from a fast learning curve, like similar to how we learn to make better cars. The challenge is in the point source capture, similar to Petronova project, we have 12 to 15 volume percent CO2 plus minus, depending on which process you're talking about. But here we only have 400, maybe 415 parts per million CO2 in the air at this time. And because of that, target is quite different as well. You cannot really capture 95% of CO2 from that stream. You'll be capturing about 60% of CO2, and that will be the target. Other challenges for systems and materials development is also interesting because amount of air you have to process to capture that CO2, the same ton of CO2 is so much more air. So it is not possible for us to compress all that air. So you need to have very low pressure drop in any of your direct air capture systems. Also, you're capturing CO2 from the stream, which is air, has high oxygen concentration. And because of that, your material inside your direct air capture system has to be very robust at high oxygen concentration, and having higher oxidative thermal degradation, thermal stability is very important for your materials for longevity. And this system, as you can see in this photo, it will be sitting outside and then working with the environment, which is your reactant air is coming in, so that you need to deal with some dry days, rainy days, hot days, cold days, so that fluctuating reacting conditions, including humidity is very, very important, and other impurities. So I started looking into this. I think there are a lot of good direct air capture companies to learn how to move air efficiently. I think the next generation of big challenges and opportunities are all about materials, how to develop materials to put it into these systems. So I started thinking about our material gnomes, because gnomes has almost zero vapor pressure. I can leave the cup of that material outside in the air for years and years, and still it won't evaporate. Only thing is it might collect all the dust. So what we started thinking was, well, if we can make low pressure drop system, which is kind of protecting gnomes, maybe it can be a great direct air capture materials. So start working with the Yong Zhu, who have not worked on CO2, but now he does a lot of that research now, because this project funded by Department of Energy is, he's been doing gas-assisted electrospinning for fuel cell applications. But what I was asking him was, can we make something similar to furnace filter-like system, which we can really reduce the pressure drop across, but we can encapsulate our materials into these fibers. They can be installed much easier. But I also worked with Michelle Kidder at Oak Ridge National Lab, asked her, can you give us the shell material, which is highly porous, but I had one more request. Can you make it hydrophobic? So hard material called PIM1, PIM2, these are very porous, but at the same has these fluorine groups making them hydrophobic. Well, so what we hypothesized was that we might be able to selectively reject the water while letting CO2 in to capture CO2 within these fiber systems. Here are some of the SEM image of our fibers we actually made with the gnomes inside. And this is the data of CO2 capture. There's a huge boost in CO2 capture capacity. And some of the other gnomes material we also use, if you look at the top, there are 2 gnomes on the left and 2 polymer, just electrospun fiber with polymers PEI and TIPA we started with. And by looking at all these, we were able to make fibers. And all of them, especially 3 of them, both gnome-based electrospun fiber were very hydrophobic. Even PEI-based one was hydrophobic somewhat, but then by the time TIPA, it wasn't hydrophobic. The reason is the way we make electrospin fibers, TIPA was too tiny, very short, a smaller amine polymer, so that it was migrating towards on the surface. And you can kind of see in these SEM images so that on the surface, the TIPA was exposed, making the surface hydrophilic. So if you want to selectively reject water during direct air capture, definitely TIPA is not the good option, but gnome-based system seems to be fantastic at keeping it hydrophobic while keeping all the gnomes-based these CO2 capture materials encapsulated within this fiber system. We did test between direct air capture systems as well as 100% CO2, just looking at the CO2 capture capacity. And if you want to look at the left-hand side, it's very interesting that the non-PEI case and PEI case work very competitively. But PEI, remember I was showing you that PEI is not thermally stable for over multiple cycles. So this shows that non-PEI-based electrospun fiber, this fiber encapsulated system, has really great potential for direct air capture. So next, I want to speak a little bit about combined CO2 capture and conversion. At the end of the day, once capture CO2, we need to convert. So one of the areas of CO2 conversion, people have been working quite a bit using renewable energy, as I've shown you in the whole new circular carbon economy, is electrochemical reduction of carbon dioxide to a wide range of products. You can go to CO, formate, as well as even C2 plus material or products if you're using copper-based catalyst. A lot of my colleagues are working in this area, looking at how to develop new catalysts, catalyst morphology, even reactor systems. But not that many people really focused on electrolyte design. In fact, the CO2 solubility in regular conventional electrolyte is very low. So then you can go to 2 different options. Either you can go to gas diffusion electrode, minimizing all the dissolution issues, or you can make the electrolyte better, increase the solubility of carbon dioxide. That led me to kind of think about what if we use this gnome system we developed as additives for electrolyte. Perhaps we can use gnome-based electrolyte as a medium which hosts both CO2 capture and conversion in the single reactor systems. So we start thinking about this 2 fluid system. Let's go to very simple 2 system of water mixed in with. Left-hand side is just with the gnomes. Right-hand side is the polymer we started with. You can do it HPE or PEI, whatever polymer we've been using. What we thought was, since right-hand side, you only have an untethered polymer, we thought that it should have, the polymer-based electrolyte should have lower viscosity and higher conductivity. Only thing I was hoping was our gnome-based system, only difference is it has a whole bunch of nanoparticles running around along with other stuff. We thought if it can perform as well as the polymer-based system or slightly less, we'll still take it. But then results was exactly opposite. We found that conductivity was higher and then viscosity was lower for the gnome-based electrolyte. So we were getting a little confused. Why? Because we definitely have nanoparticles compared to the other case. So we went back a number of times, but still we were seeing the same trend. So we went to Argonne National Lab and then measured the USACS data. And a lot of USACs done in norms-based systems or something similar were showing a lot of signal at high Q range because these are very small nanoscale systems. But we also start to see signals at low Q range, which is indicating that there's chunkier stuff in your norms-based electrolyte. Analyzing these different sections with our colleagues at NIST, this is not what we think. In the bulk fluid, in naked eye, this norms-based electrolyte is a very clear liquid. But if you zoom in, there's agglomerates at micron scale. If you even zoom in, there's aggregates in the tens to 100 nanometer scale. And because of that, instead of even distribution of these norms, single fluid units everywhere, they were interacting with each other more than we thought. And in fact, within this norms-based electrolyte, there's a different pathways for transport and some even channeling. So this became very interesting coupled reaction kinetic studies in these systems. And we also did the SANS data results as small angle neutron scattering, and then our colleague Mark Degman, and we found out that this tethered polymer system is a little more complex than we thought. Initially, all our known systems, we thought that all the polymers were tethered onto the surface. But whenever we calculated graphene density, it was higher than we thought. What we found out was that there are polymers. Now, in the tethered polymer, in between tethered polymers, there is a polymer stuck in between. And those polymers doesn't get detached from that region, but it can swell or have a different conformation depending on secondary fluid, which is we start to calling these polymers interacting polymers. And those are kind of a pseudo system of norms so that the overall size of the polymer, the norms, and then how norm interacting with secondary fluid and ionic species and even CO2 was highly depending on how interacting polymer and tethered polymer are interacting with them. So it was very interesting looking at this. And because of that, now we had to look at once we bubble CO2, how much CO2 we can load it into this norms-based electrolyte. As I mentioned, this is the water system, just conventional electrolyte, very low solubility of CO2. As we increase the amount of CO2 loading, you have increase the norms loading, we have a lot more CO2 can captured and loaded onto this norms-based electrolyte. And that's really depending on physisorption versus chemisorption. Of course, chemisorption is a lot higher than physisorption. And conductivity also get impacted if you do chemisorption because we are now making a lot of ionic species, so we actually enhance the conductivity of the overall system. Now we just have to do the electrochemical conversion of that CO2 loaded into these different electrolyte, and we were collaborating with the Feng Zhao's group at University of Delaware. And when we started with this just potassium bicarbonate electrolyte, no norms, and compare that with these two systems of one with the PEI-based norms, the other one with HPE-based norms. So this is physisorped CO2. This one is a chemisorped CO2. And looking at across the different potential, there's always competition between hydrogen evolution reaction versus CO2 reduction. And it's a very typical data. And you can see that the PI-based and norms-based electrolyte is very different compared to HPE-based, somewhat similar. But we had a lot higher per pass conversion of CO2 because we are loading a lot more CO2 to the electrolyte. And the reason this conversion is lower and the Faraday efficiency is different is because the carbamate is not electrochemically active. So I don't have data here, but by increasing the reaction temperature, now you release the carbamate CO2 into CO2, which is electrochemically active, you can convert back to much more CO2 conversion to CO at higher temperatures. But this kind of led to a lot of interesting discussions because as shown here, CO2 loading is higher, but how CO2 is delivered to the surface of the catalyst? Our hypothesis too, because Faraday efficiency with and without norms were slightly different, in some cases quite different. That might be because One mode of CO2 delivered to the surface of the catalyst is NOMS serving as internal reservoir of carbon, release that CO2, and that released CO2 gets absorbed to the surface of the catalyst. That should not change the Faraday efficiency. But what if CO2 delivers that CO2 to the surface of the catalyst and then kind of hovers around during the CO2 conversion? Then maybe this interaction with all the tethered polymer on NOMS will bend CO2 just right so that its conversion is taking very different pathways. This could change the Faraday efficiency. So in order to really understand where NOMS is and how they interact with the electrolyte electrode interface at the interface, we went to NREL. So my colleague, Wilson Smith, has a very interesting system of ECAFM, really understanding the surface at the interface and what's happening in the electrolyte system under applying the different potential. So this is a typical, or we started with silver foil, which is a very simple system. And this is the silver foil just with water on top. And there's some roughness to it, and you can actually get the roughness measurements as well as modulus and deformation. And modulus and deformation are going to tell us, compared to this base case, what's on the surface. If there's a specific absorption of polymers onto the surface, you will have very different modulus and deformation, which we saw. So this is second system with silver foil with PI in the solution, and you can see that it's much softer on the surface, so there's a higher deformation, and modulus is lower too. So here, if you look, let's look at the no applied potential with PI we started with, and as we hypothesized, more likely PI gets absorbed onto the surface of the electrode, and because it's on charge, it will be certain conformation. And if we apply the potential, what we found out was these polymers get collapsed onto the surface of this electrode, which means that this case and this case with and without the potential, you have very different transport behavior on the surface, and interaction between this polymer in electrolyte and electrosurface will be very different. But interesting thing happened when we had the same system. Now we saturated this entire system with carbon dioxide. And all this carbon dioxide surrounding this polymer, PEI, as we applied the potential, it was very different. Its deformation did not change, meaning the conformation of these polymers on the electrode surface wasn't changing much. So when you try to really understand what's happening at electrode and electrode interfaces, having the system with the electrochemical potential in AFM or any other measurement in situ is very important. So these information will tell us how CO2 gets delivered to the surface of the catalyst and converted to products. So overall, we are kind of looking at not only looking at power sector decarbonization, we really need to thinking about how to create a whole new circular economy, looking at the direct air capture, direct ocean capture, and all the hard to decarbonize industries, and also create different reaction pathways using only renewable energy eventually to creating the whole new circular carbon economy. But last few minutes, I want to talk to you a little bit about clean energy transition. Because the whole reason we are working on carbon management is because we realize that fossil resources, which we've been really enjoying creating the whole modern society and industries, are creating the climate change and many other issues, environmental concerns. And if we knew, when the first day we designed the coal-fired power plant, we knew all these problems, perhaps engineers and scientists would not have designed the same system. Maybe we were capturing CO2 from the day one. I hope that's the case because we solve problems. But how about clean energy? Clean energy transition towards the renewable energy, solar and wind and so on, is it really clean? That's one of the first questions we should ask today so that we don't make the same mistake we did with the carbon or fossil resources. I think many of you heard about last decade or so, we've been talking about how metal, rare earth elements and other metals are really, really needed for clean energy transition. And it's really linked to geopolitical issues and China, US constraints and frictions and all that so on. And if we can get the rare earth elements from domestic resources, it would be really important for our sustainable and clean energy transition. So in fact, in not only REE, we now have something called energy relevant critical minerals. These include all the rare earth and nickel, lithium, cobalt, even copper, and many other metals, whatever we need to create the entire infrastructure and energy systems for renewable energy. So where do we get those? And I think that's very important. So remember that photo on the top right-hand side? These are serpentine tailings people have been using for carbon sequestration, making solid carbonates. But before they were called for carbon mineralization feedstock, they were called nickel ore. It really has nickel in it, and we've been mining these tons and tons of these materials to get nickel out. And on the left-hand side, this is one of the few man-made structures you can see from the space. This is copper mine in Utah. And if you look into your phone, cell phones have about 16 to 18% copper in it, quite high concentration. And clean energy transition requires a lot of batteries, and batteries require nickel, and nickels are used everywhere. So let's think about how much of nickel and copper we have in these natural resources. When I checked, I was really shocked because in copper mine, we only have a 0.44% weight percent copper. And nickel ore, we only have 0.2. We literally move mountains every day to do all the clean energy transition. Okay, we don't like all this fossil fuel making CO2 emissions and climate change and all that. But do we like mining? Is mining really environmentally sustainable and friendly? No. It does not mean we should not do clean energy transition, which means that we need to think about this while we are doing clean energy transition so it can be truly clean. So at the same time, because there's only 0.2 and 0.44%, sometimes we have to even do material circularity of all these energy systems, which requires a separation of metals in the presence of many competing metals or many other things. So it also calls for new type of and for new challenges associated with separation technologies. So a lot of research we do is related to reactive separation, and that is linked to converting conventional mining to sustainable mining, which I'm not going to talk about in detail, but at the end, we need to look at a wide range of sources, not only primary ore, but we have to really look into even electronic waste and many other secondary resources for metal recovery. And if we can tie that with carbon management, it would be the really sustainable mining. So one of the challenges is separation, as I mentioned. And biology does it really well when there's a complex systems and you want to target only one particular things at a time. So on the right-hand side is one of the examples of biology really trapping cerium in the middle of many other metals competing for that binding site. There's a multiple binding sites and create the right cavity. So we thought it was a really interesting approach, and we can mimic this by designing structured ligand systems. So here is our design. We will have a scaffold and then putting the ligands at the right locations. And the reason we were thinking about this is that this scaffold can be directly tied to gnomes I was talking to you about, which I'm not going to talk about too much today, but this backbone can be created by using our gnomes. But by putting the right binding ligands, which with the binding energy, but create the pocket just right size for the target metal, and we can have multi-dentate system, ligand system, which can capture and release and catch and release the target metal. So we really wanted to compete and see competition between calcium and magnesium and cerium, for example. And here are some of the example with the different binding energy and data showing the cerium versus sodium versus calcium versus magnesium. In all cases, we were able to selectively grab cerium in the presence of high concentration of sodium, calcium, and magnesium. This does work. And one of the reasons is that not only binding energy was strong enough, but shown in this DFT calculation, cerium is very snug into this cavity of structural ligands, so that connecting to the all 7 binding sites. But in the case of calcium and magnesium, they don't get the full binding of all binding sites, so that it's kind of dangling. And because of that, we were able to get really very selective cerium capture in the presence of calcium and magnesium. And by keeping calcium in the solution, we were able to do the carbon mineralization in the downstream. So another important thing is that this system will be catch and release and catch and release. Again, we need to regenerate and release that cerium back out, or rare earth elements. So when we are looking at the binding on and off events, it's between pH of 5 to 8. And this is really great pH range because we can actually simply capture cerium or other metals, target metals, and then by bubbling CO2, we can release that the cerium back out. And then by bubbling air, we can go back up and start to regenerate these structural ligand systems. And this is real green chemistry. So in summary, I hope that I showed you some of the examples of how to design multi-hybrid, multi-scale materials in different form factors with the different chemical functionalities to deal with carbon capture, utilization, and storage. At the end of the day, the climate change is such a problem at scale, which you want to change the way we harvest and use and store and manage carbon throughout both engineered and natural system. We need to have all the technologies available out there. And electrification, reactive separation, and absorption behaviors will play a really important role in the future. And we need to create the new pathways to existing chemicals, but even new pathways to new chemicals. But we should do all that by keeping our environment and humans within system boundary to be sustainable. Here are my funding agencies and my students, and I'll be happy to answer any questions. And thank you.
Thanks very much, Alissa, for your talk, telling us about your work. And it was also nice to kind of see the kind of overview of all of the aspects of CO2 management that we need to kind of keep in mind and consider. So yeah, if you have time for a few questions, a couple have come through. We have one asking about the encapsulated known PEI materials. Do you have any or information, or have you done any work on kind of the energy required for regeneration or any kind of CO2 working capacity values?
Yeah, CO2 working capacity is similar to a lot of amine functionalized materials. There are a lot out there. The main difference is that our NOM system has the PEI materials with our nanoparticles, which is about 15 weight%, is inert, right? Unless it has its own function. So per solvent, we capture less CO2 slightly, but it's really important to have our nanoparticle because what we learn is over 100 cycles is so robust. For you to not only look at the single pass, like a catch and release, capture and regeneration of materials, energy penalty is important, but economics of the CO2 capture, regardless direct air capture or point source capture, is long-term stability and robustness of the solvent is extremely important. So I think we gain from there. But also recently, there's a lot of discussion on how to regenerate CO2 capture materials. I didn't present it here, but we are preparing manuscript on non-thermal energy transfer. This is quite interesting when you talk about the direct air capture, because if direct air capture can be installed many different places, which is quite far, in some cases, middle of nowhere, near injection site or utilization site where there's no power plant. We've been always counting on waste heat, about 120, 140 degrees C regeneration using waste heat for many years, many decades. But what if there's no power plant, no waste heat? So first way, like a mean of providing energy might be renewable energy, which is not heat, is electrons. So there's a lot of recent studies done by national labs and academic groups, including mine, looking at how to do non-thermal energy transfer for CO2 solvent regeneration as well as CO2 conversion. Then it becomes very interesting. So if we can somehow target only, for example, in terms of carbamate, if we can only transfer energy to carbamate site and release that CO2, it could be minimum energy requirement because you don't need to heat up entire reactor, entire system to get to 120, 240 degrees C. Chemical engineers are very used to isothermal operation of reactors, right? Isothermal reactor here and reactor here. So we capture CO2 at either ambient temperature or 40 to 60 degrees C. And we increase the entire reactor system to 120, 140 degrees C to release. But if we can do really targeted energy transfer, it could be the minimum energy penalty. So we've been looking at the, for example, easiest one we can consider, a lot of people are doing now is microwave. So we are making NOMs with the microwave active materials incorporate into the system. We were able to reduce the CO solvent regeneration time from hour to half an hour, which is stream stripping or indirect heat transfer, to only less than 2 minutes. So you save so much time, and also total amount of energy will be going down because now CO2 capture and solvent regeneration ideally will happening at the same temperature. So I think that's the future direction we should really consider, whether we can run these reactors just really targeted delivery of energy for regeneration.
Thank you for your detailed response. I hope that answers the question that came through. Targeted kind of heating is quite interesting when you were talking about it. I was kind of imagining if you send enough infrared radiation at the correct wavelength, you might be able to explode off the CO2, because I guess that has some kind of frequency where it absorbs that energy. But anyway, moving on from that, we also had another question coming through about other research that you do in your group. Have you investigated these materials, for example, in mixed matrix membranes at all?
Mm-hmm. I did not do as much, only one publication collaborating with Junfeng Wang at Chinese Academy of Science, IPE in Beijing, but I think a lot of people are looking into it. One of the reasons I did not look into mixed matrix membrane is for direct air capture, I don't think we can use membrane systems. But as you can see in many of our systems, so in a sense, for me, SIPS is very similar to mixed matrix membrane, but we just don't use it as a membrane. I think the benefits of membrane of a highly porous materials and all these things are employed in our solvent design, but we don't work on the membrane. But I think for other types of CO2 capture or many different separation systems, I think it's very interesting to do reactive separation using those membrane systems.
Thank you very much. And we have one final question, which I think you answered earlier, about kind of the regeneration and reactivation of these materials. And I think specifically with regard to the CO2 utilization process, so when you're doing capture and simultaneous conversion, do you see, I guess I'm editorializing a bit on this question, but is your reaction rate fast enough such that you don't end up always saturating the material, the adsorbent side, or do you need to at some point regenerate the material and start again?
Yeah, that's interesting. Well, I don't think we have that issue yet, just because the CO2 conversion in the electrochemical cell is still relatively slow, or the per pass conversion is not high enough, so that even regular conventional electrolyte is good enough at this point. So we are kind of oversaturating it. I think at the end of the day, will be kind of, you have to tune the system so that the best case scenario, so looking at the PEI versus NOMS versus the ether group, HP based NOMS, HPE1 is total amount of CO2 loading is lower, but binding energy is less. It's just a simple Lewis acid-based interaction. So you kind of shuffle the CO2 on the surface. So there is a faster conversion, but at the same time, you bend the CO2 just enough so that it gets easier to convert. So activation energy changes as well. In terms of PEI, you do need to regenerate. So I think the binding energy of CO2 capture material, if you're trying to combine capture and conversion, you need to rethink about it, and the rates as well. So I think instead of a total loading, you have to match the conversion, which could be the rate limiting step, and then match that rate, and then keeping that energy low enough so that whatever bound CO2 to your CO2 capture material is already activated or reactive to either electrochemical conversion or thermochemical conversion. That will be the best way. So some of my colleagues are looking at dual functional materials, looking at how to put catalyst and CO2 capture absorption site on the same system. We are doing with electrochemical systems. I think now binding energy of CO2 and rate of CO2 capture has to be further optimized. And that's one of the areas we are very interested in. Good question.
Yeah, thanks very much again for your answer. And I think highlighting the optimizability, if that's a word, of your materials, I think can really help with that. So with that, I'd like to thank you again for your talk. I'm now going to hand back over to Nicholas Wilkins, who will wrap up the session for today.
Okay. Thank you, Professor Park, for your presentation, structure, and transport behaviors of liquid-like nanoparticle organic hybrid materials designed for combined carbon dioxide capture and conversion. We also thank all of our attendees for joining this webinar. We hope that it was both educational and enjoyable. An edited version of this webinar will be posted on the IAS YouTube channel and Bilibili with an announcement on the IAS Twitter feed. The hope is that the work discussed today will be a useful resource for the absorption science community in the future. The next confirmed IAS webinar will be given by Susana Garcia on June 14th at 2 p.m. UTC, the same time as today. Announcements regarding the next webinar and other IAS online events will be posted on our Twitter feed and through the IAS mailing list. With that, we thank you for joining us, and we hope that you join us again soon in the future.